beyond the reach of traditional microscopes, and within theoretical physics lies a frontier not so much of remoteness as a possibility in understanding. This frontier is challenged not by physical barriers or vast distances, but by the depth of its implications and the invisibility of its scope. Welcome to the quantum realm, where the building blocks of technology and reality behave quite differently from anything we've ever encountered in our macroscopic world. Quantum mechanics is a phrase that excites the intellect and baffles the mind with its strangeness. Here, particles can exist in several places at once. They can spin in opposite directions at the same time. They can be entangled in the vastness of space, acting in concert with no apparent connection. These bizarre behaviors are at the heart of a technology that could revolutionize our world: quantum computing. At the heart of this technological storm lies a concept so revolutionary and yet so elusive that it challenges our very perception of information and reality. By traveling the quantum frontier, we enter a space where information is not just processed, but exists in states that defy classical logic. Here, quantum bits or qubits can store many possibilities at once. Compared to the simple bits of today's digital devices. But how to preserve information in a system that loses its essence at the slightest interaction with the environment? Scientists may have some answers to that question, because quantum mechanics does more than just redefine computing. It encourages us to rethink the cosmos, intertwining with the fabric of space and time in enigmatic phenomena such as black holes. These cosmic anomalies are not mere objects, but the key to understanding the quantum puzzles that hold the secrets of the universe's information storage and retrieval systems. Join us on our expedition, an expedition to the frontier of quantum mechanics exploration that may ultimately redefine the meaning of computing, data protection, curing disease, and perhaps understanding the very fabric of reality itself. So you and I are gradually entering a new era of computing that transcends the binary landscape of classical computing, where data is processed as a straight series of zeros and ones. In contrast, quantum computing works with qubits, which can embody zeros, ones, or both at the same time, utilizing special properties of quantum mechanics to perform complex computations at unprecedented speeds. However, the quantum world is as fragile as it is powerful. One of the main challenges in developing quantum computers is creating and maintaining quantum memory. Unlike classical digital memory, which can reliably store information and retrieve it at will, quantum memory is extremely fragile. Any interaction with the external environment can cause quantum information known as quantum states to decohere, that is, erase the stored data. It's like trying to hold a spinning coin on its edge. This susceptibility stems from the fundamental nature of quantum memory. It is not simply a matter of storing data, but of preserving complex quantum states, which are the basis of the potential of quantum computing. Herein lies the paradox at the heart of quantum computing: no cloning theorem. This theorem is a unique rule of the quantum world and states that it is impossible to create an exact copy of an unknown quantum state. In the everyday world, if you want to prevent data loss, you can make copies of it. But in quantum computing, it's impossible to make an exact copy of a qubit containing unknown information. This rule's a serious obstacle, because it means that traditional methods of data protection and error correction, like backups, they simply don't work in the quantum domain. Engineers and physicists are now tasked with developing innovative strategies to combat these problems. They're using quantum error correction techniques that involve entangling qubits, linking them together in complex ways, and allowing the system to detect and correct its own errors without having to directly measure the quantum state. Now, these methods don't just preserve information, they preserve the very essence of quantum behavior. But how can the very gravity wells where not even light can penetrate and quantum computing be related, you ask? The intriguing connection between black holes and the burgeoning field of quantum computer science begins with one deep mystery they share in common. Stephen Hawking and Jacob Bekenstein, two titans of theoretical physics, once proposed groundbreaking ideas about black holes that have profound implications for modern quantum computing. In a thought experiment, Hawking hypothesized the black hole information paradox, which poses a profound dilemma. What happens to information when it falls into a black hole? Does it disappear forever, or does it persist in some form? This question is analogous to the quantum computing problem with data integrity and loss. Just as information must be preserved when it crosses the event horizon of a black hole, quantum information must be preserved in the unstable environment of a quantum computer. So how much information can a black hole store? Bekenstein, in turn, presented the concept that the entropy of a black hole, in fact, its information content, is proportional not to its volume, as one might expect, but to the area of its event horizon. But how can a surface store information, you may ask? After all, you need some kind of structure. You need atoms or something else that can store bits of information. It turns out you can calculate that a black hole stores information in bits. The amount of information is equal to the surface area of the event horizon in Planck square units. Planck square units are the smallest measurable scales in the cosmos. These units were named after Max Planck, mark the limits beyond which classical theories of gravity and space begin to break down and quantum effects become dominant. Planck units serve as a bridge in our understanding of quantum and cosmological scales, providing a framework that helps us quantify the universe in the most minuscule dimensions imaginable. So, why is the information content of a region of space equal to the surface area surrounding that region and not its volume? Consider this analogy to better understand the unconventional way information is stored in a black hole. Imagine that your room is not just a library, but a magical library where your entire collection of books can be encoded simply on the wallpaper that covers the walls. Here, instead of measuring the volume of the room to determine how much it can hold, we look at the surface area of the walls. And this radical idea reflects how black holes store information, but not in their vast void, but on their outer surface at the event horizon. This leads us to the holographic principle, which may seem like science fiction, but it's a serious scientific theory inspired by the thermodynamics of black holes. A hologram, colloquially speaking, is a flat surface that contains all the data needed to display a three-dimensional image. If you apply this to the universe, a startling possibility arises. Everything you see around you, from your cup of coffee to the stars in the sky, could be a projection of information encoded on a distant two-dimensional surface. The Juan Maldacena model, known as the Anti-de Sitter Conformal Field Theory Correspondence, or ADS-CFT, goes further. It purposes that the type of universe described by Einstein's theory of gravity, negatively curved and seemingly limitless, could be equivalent to a gravity-free quantum field theory defined at the boundary of that space. Essentially, it's as if there were a boundary at the end of the universe that contained a two-dimensional description of all three-dimensional events occurring in it. This revolutionary idea suggests that our understanding of space and time, however intuitive as it may seem, may be an emergent phenomenon from a deeper, more fundamental reality. The implications for quantum computing are profound. By mimicking the natural holographic data storage observed in black holes, engineers will be able to create quantum systems that are both stable and powerful, capable of performing computations impossible for a classical computer. As we move closer to mastering quantum computing, its impact on our future is becoming increasingly clear and promising. This technology doesn't just increase the speed of data processing, it expands our ability to solve problems previously thought unsolvable. Cryptography, medicine, space exploration. It's just the beginning. In the field of cryptography, quantum computing is a double-edged sword. On the one hand, they pose a significant threat to existing encryption methods. Traditional security protocols rely on the complexity of factorizing large numbers, for which quantum computers are exceptionally well suited. This capability means that most existing encryption methods can become obsolete over time, leaving data vulnerable from your personal correspondence to access to your bank account. However, the same ability opens up the potential for quantum cryptography, which can provide a level of security that's fundamentally unbreakable. Quantum key distribution uses the principles of quantum mechanics to create secure communication channels. Unlike traditional keys, any attempt to eavesdrop on a quantum key changes their state, thereby revealing the presence of an attacker. This method could revolutionize the transmission of sensitive information, making our data secure against even the most sophisticated attack. In medicine, the impact of quantum computing could be revolutionary. The ability to accurately model molecules and biological processes opens new horizons in drug development. Currently, the development of new drugs is a long and expensive process, often taking more than a decade. Quantum computers can significantly speed up that process by predicting the properties of complex molecules and their interactions with the human body more accurately than ever before. One interesting example is the use of quantum computing to develop treatments by modeling the human lung on a chip. This innovative approach, developed by a Swiss startup, uses quantum computing to model human lung cells on a microchip. These cells can be mechanically activated to mimic the behavior of a real lung. And that allows researchers to observe how the drugs would interact with human tissue in real time. Imagine a world in which we can model the human body in minute detail on quantum computers, creating digital twins that doctors could test treatments tailored to each patient. That approach could not only speed up development of new drugs, but also improve their efficacy and safety many times over. It represents a shift towards more personalized medicine where treatments are optimized for each patient's unique genetic characteristics. Beyond healthcare, quantum computing also promises to revolutionize energy efficiency across sectors. Its ability to solve complex logistical problems and optimize systems can lead to more efficient use of resources. For example, quantum algorithms have already improved cargo movement at the Port of Los Angeles, increasing throughput and reducing energy consumption. Space exploration can also benefit greatly from quantum computing. Navigating vast expanses of space requires processing vast amounts of data for trajectory alignment, system diagnostics, life support management. Quantum computers could improve the ability of spacecraft to perform these tasks autonomously, making deep space missions more feasible. In addition, quantum technologies can improve our ability to predict and understand space weather, protecting astronauts from harmful radiation and preserving critical satellite infrastructure. Research into black holes and quantum mechanics is not just a theoretical fad. It's shaping the very tools we expect to revolutionize our future. The insights gained from studying these cosmic mysteries are helping to inform and advance algorithms that will one day be able to manage our data, cure our diseases, and even guide our research into the uncharted reaches of the cosmos. So, quanta, in simple terms, are the smallest possible units of any physical property involved in an interaction, such as energy or matter, such as particles and photons. In classical physics, everything seems smooth and continuous, but at the quantum level, things like energy move in tiny discrete packets, such as quanta. That's why there are quite a few different methods of quantum computing, each exploring unique approaches to using these tiny units to generate enormous computing power. One of the leading techniques in current quantum computing research involves superconducting circuits. Companies like Google, IBM, and Rigetti are investing heavily in this technology, which uses supercooled circuits to minimize energy loss and maximize efficiency. These circuits operate at temperatures near absolute zero, allowing quantum states to persist long enough to perform complex computations. Another well-known method uses trapped ions as qubits. Companies like IonQ and Quantinuum use this technique where ions are held in space using electromagnetic fields and manipulated with lasers to perform quantum operations. This method boasts longer coherence times, meaning that quantum states remain stable for longer periods of time, although the speed of operation is generally slower compared to superconducting circuits. Photonic quantum computing is also gaining momentum with qubits encoded using photons, particles of light. The approach promoted by companies such as Xanadu and startups affiliated with academic groups operate at room temperature and use the properties of light to perform quantum computing. Recent advances include Xanadu's development of the Borealis chip, which uses a novel method of manipulating groups of photons to gain quantum advantages. In turn, topological quantum computing, which has emerged from a more theoretical framework, offers a new approach to utilizing quasi-particles, particles that arise from interactions within a material. Microsoft has been a key player in this field, exploring ways to create and manipulate these quasi-particles to create qubits that are naturally immune to external perturbations, potentially solving the problem of quantum decoherence. In addition, one quite revolutionary approach to quantum computing is rapidly gaining momentum. And this new method, using atoms held in optical tweezers, represents a significant leap forward in our quest to harness quantum mechanics for computing power. Let's take a closer look at this innovative technology and learn how it has the potential to revolutionize the field. Optical tweezers, a tool that uses focused laser beams to capture and manipulate particles, are nothing new in physics. But their application in quantum computing is a new and rapidly developing frontier. By using lasers to capture individual atoms, scientists create qubits that are less susceptible to interference and easier to control than traditional methods. This technique is based on the unique properties of atoms, being small and electrically neutral. They naturally avoid mutual interference that interferes with other types of quantum bits. This reduction in noise and interference is crucial to maintaining the coherence of quantum information, which is an ongoing challenge in quantum computing. A recent breakthrough in February this year involved the use of microlens arrays, which allows a significant increase in the number of atoms that can be manipulated simultaneously. These arrays allow thousands of atoms to be precisely arranged in regular order, each held in place by its own microscopic laser trap. Researchers have successfully used this technique to arrange more than 1,000 atoms with remarkable precision. These atoms are not just statistically held, they're dynamically controlled, ready to perform complex quantum operations. The term supercharging accurately describes the improvement this method brings to quantum computing. By aligning two layers of microlens arrays and superimposing laser traps on them, scientists create a dense grid of atomic qubits. The arrangement not only increases the initial number of qubits, but also improves their overall stability and homogeneity. Each atom trapped by this method can potentially serve as a quantum bit. The precision of this approach allows each qubit to be individually addressed and manipulated, opening the way to complex and large-scale quantum algorithms that were previously unattainable. When this new method is compared to existing technologies like superconducting qubits and ion traps, the atoms in tweezers approach offers significant advantages in scalability and error reduction. Its ability to scale rapidly to thousands of qubits makes it a formidable competitor to better-known technologies. Looking ahead, the potential to scale this technology to 100,000 atoms and beyond is not just optimistic speculation, but a very realistic goal. Achieving this scale could bring quantum computing closer to commercial viability, allowing complex problems from cryptography to material science to be solved. As we conclude our journey through the quantum frontier, we find ourselves at a pivotal moment where quantum computing is moving from theoretical research to practical applications. The XPRIZE Quantum Applications Competition epitomizes this transmission, presenting a challenge with a significant $5 million incentive to spur innovations that apply quantum computing to real-world problems. Over the next 3 years, teams from around the world will explore and demonstrate how quantum technologies can revolutionize healthcare, materials science, energy, and other fields. This initiative not only accelerates the development of quantum technologies, but also emphasizes the potential of quantum computing to solve humanity's most pressing problems. By pushing the boundaries of quantum computer capabilities, XPRIZE aims to stimulate the transition from experimental quantum applications to everyday tools, making the fields of quantum mechanics accessible and useful to society at large. Imagine being able to harness the power of the sun, which has been the lifeblood of our planet for billions of years. Its energy, produced in a process known as fusion, illuminates our world and sustains life. But what if we could replicate this process right here on Earth? What if we could create our own miniature suns to power our homes, our cities, and our world? Sounds like science fiction, doesn't it? But what if we told you that this is not a distant dream, but a reality that scientists have been approaching for decades? In the heart of California, at the Lawrence Livermore National Laboratory, a group of dedicated scientists work tirelessly on this mission. Their goal? To accomplish nuclear fusion, a feat that could revolutionize the way energy is produced and pave the way for a future of clean, limitless power. And quite recently, at the end of last year, there was a breakthrough that could have changed everything, illuminating our future. Imagine our star, the Sun, 93 million miles away in the vast expanse of space. It is a giant glowing ball of gas that's incredibly hot. Have you ever wondered what makes the sun shine so bright? The answer is both simple and complex: nuclear fusion. In simple terms, nuclear fusion is the process by which two light atoms combine to form a heavier atom. It's like taking two small Lego blocks and putting them together to make a bigger one. But there's a catch. When these atoms combine, they release a huge amount of energy. And they release so much energy that it allows this energy to power the sun and make it shine. Now you may be thinking, that sounds great, but what does that have to do with us here on Earth? Well, if we could replicate this process, we could potentially create a virtually limitless source of clean energy. Imagine your house, your city, and even your car being powered by the same process as the sun. That is what fusion promises us. But this idea is not new at all. Scientists have been dreaming of harnessing the power of fusion for decades. In fact, the concept of nuclear fusion was first introduced in the early 20th century by physicists like Albert Einstein and Hans Bethe. Over the years, there have been many attempts to achieve fusion, from Project Sherwood in the 1950s to the first tokamaks in the 1960s, and the construction of modern facilities such as ITER and the National Ignition Facility in the U.S. Each of these efforts brought us closer to the goal of achieving fusion. Although there have been problems and setbacks along the way, the dream of harnessing star power has never faded. And now, with the recent breakthrough at Lawrence Livermore National Laboratory, we may be closer than ever to making that dream a reality. Just imagine a world in which the light in every house, street, and city is powered not by coal or gas, but by the same process as the stars. As we discussed earlier, fusion is a process in which two light atoms combine to form a heavier atom, releasing huge amounts of energy. But what makes the process so special? Why are scientists around the world so interested in it? Today, most of our electricity comes from burning fossil fuels like coal and gas. These processes release harmful greenhouse gases into the atmosphere, contributing to climate change. Such resources are also finite, which means they will run out sooner or later. But fusion offers another way. Fusion is fueled by hydrogen isotopes such as deuterium and tritium. Deuterium can be extracted from seawater and tritium from lithium, which is abundant in the Earth's crust. This means that the fuel for fusion is almost limitless. And remember, the energy released by fusion is enormous. Just 1 gram of fusion fuel can produce the same amount of energy as 8,000 gallons of gasoline. That's like driving around the Earth more than 300 times. Fusion could generate huge amounts of energy without the carbon emissions associated with fossil fuels. This could help us fight climate change and move towards a more sustainable future. The outlook for fusion energy extends beyond the scientific community. Political figures such as U.S. Senate Majority Leader Charles Schumer also recognizes its potential. He stated, "This breakthrough is a giant leap toward making fusion power a reality. It marks the beginning of a new era in energy production that is cleaner and virtually limitless. The potential for our economy and the environment is enormous." With the stakes so high, it's not surprising that the fusion race is often compared to the space race of the 20th century. But achieving nuclear fusion is not easy. It requires incredibly high temperatures and pressures, such as those found in the heart of the sun. Also on top of this, for many years, the energy required to start a fusion reaction exceeded the energy it produced. But this is where the Lawrence Livermore National Laboratory and the National Ignition Facility come into play. They're working to make fusion a reality, and their recent breakthrough could be a game changer. Imagine a place where the world's brightest minds come together to solve some of the biggest problems facing humanity. That place is the Lawrence Livermore National Laboratory, or LLNL for short. Located in California, LLNL is a center for scientific and technological innovation. It is home to thousands of scientists, engineers, and other professionals who work on a wide range of projects, from national security to environmental science to, you guessed it, fusion. One of the gems of LLNL is the National Ignition Facility, or NIF. This is where the magic of fusion happens. NIF is the largest and most powerful laser facility ever built. It is the size of 3 soccer fields and contains 192 laser beams that can transmit more than 2 million joules of energy. 2 million joules is about the kinetic energy of a car driving down an expressway. So imagine the energy of a car rushing down a highway concentrated at a tiny point in a split second. That's the kind of energy we're talking about when the National Ignition System lasers go off. But what exactly does the NIF do? Its main task is to create extreme states of matter like those found in the cores of stars or inside nuclear weapons. It does this by focusing its 192 laser beams on a tiny target, creating temperatures and pressures that are several times higher than those at the center of the Sun. The target is a tiny capsule filled with fusion fuel, which is a mixture of hydrogen isotopes deuterium and tritium. When the lasers strike the target, they detonate the fuel, triggering a fusion reaction. But the road to this point was far from easy, as LLNL director Dr. Kim Boodle says. The quest to ignite fusion in the laboratory is one of the most significant scientific challenges ever undertaken by humankind, and its achievement is a triumph of science, technology, and above all, people. Overcoming this threshold is a vision that's led to 60 years of focused inquiry, a continuous process of learning, building up, expanding knowledge and capabilities, and then finding ways to overcome new problems that arise. These are the problems for which U.S. national laboratories were created. NIF is a marvel of modern technology and science, and it's played an important role in advancing our understanding of nuclear fusion, but it's not just about science. The work being done at NIF may one day lead to a world powered by clean, abundant fusion energy. So how did scientists achieve these results? Let's delve into the details of the achievement and how it brings us one step closer to such a future. In December 2022, something extraordinary happened at the National Ignition Center. For the first time, a man-made device achieved a fusion reaction that produced more energy than was consumed. This is known as fusion ignition, and it's really important. But what exactly does fusion ignition mean? So remember how we talked about fusion like connecting two small Lego blocks to make one bigger? Fusion ignition is similar to that, but with a twist. Instead of just joining two blocks together, you join so many blocks that the energy release starts a chain reaction, causing more and more blocks to join together on their own. It's like lining up a row of dominoes and knocking over the first one. That first knuckle knocks over the second, which knocks over the third, and so on until all the knuckles fall. Well, that's exactly what happened in the NIF experiment. The energy from the lasers triggered a thermonuclear reaction that continued on its own, releasing more energy than it took to trigger it. But achieving this has not been easy. As Dr. Arati Prabhakar, Chief Science and Technology Advisor to the President, says, "We have had a theoretical understanding of fusion for more than a century, but the road from knowledge to action can be long and difficult. Today's milestone shows what we can do with persistence." Once again, as the sun sets, we're left to wonder, what if we could harness the power of the stars to light our cities, power our homes, and grow our industries? But what would a world powered by fusion energy look like? First, fusion energy is clean. Unlike fossil fuels, it produces no greenhouse gases or harmful pollutants. This means it could play a crucial role in combating climate change and improving air quality. In addition, fusion energy is safe. There's no risk of meltdown as in a nuclear fission reactor, and it produces no long-lived radioactive waste. In the event of a malfunction, the reaction simply stops. We have an enormous supply of fusion energy. The fuel for fusion is water and lithium, which is in abundance on Earth. This means that the fusion energy can provide a virtually unlimited supply of energy, reducing our dependence on limited resources like oil and gas. But while the potential benefits of fusion energy are enormous, there's still many problems to be solved. Fusion reactions require extreme conditions that are difficult to achieve and maintain, and the technology to capture and convert fusion reaction energy into usable electricity is still in the early stages of development. However, the event itself gives us grounds for optimism. It shows that fusion ignition is possible and that we are on the right track. Thanks to continuous research and development, the dream of a world powered by fusion energy can become reality. But what does the future hold for fusion energy? Although the recent achievement of fusion ignition is a milestone, it's only the beginning. There's still a long way to go before fusion energy can be used on large scales to power our homes, cities, and industries. Future research will focus on several key areas. First, maintaining the extreme conditions required for fusion reactions is a major challenge. Second, we need to develop the technology to capture and convert the energy produced by these reactions into useful electricity. This will require overcoming numerous technical challenges, from handling the intense heat and radiation produced by the reactions to finding materials that can withstand these conditions for long periods of time. Another important step is to scale up these reactions to a size that could power a city. Designing and building a fusion power plant that could operate continuously and reliably is an important challenge. This applies not only to the fusion reactor itself, but also to the infrastructure for fuel supply, energy capture and conversion, and waste management. However, the potential benefits are enormous. Fusion energy could revolutionize our energy system, providing a virtually unlimited supply of clean and safe energy. It could help us fight climate change, improve air quality, and reduce our dependence on limited resources such as oil and gas. The road to fusion energy is a marathon, not a sprint. It will require continued investment in research and development, cooperation among scientists around the world, and the support of politicians and the public. But still, a promising start has been made. The recent breakthrough at the National Ignition Facility is a beacon of hope, lighting the way toward a future based on clean, abundant energy. And the farther we look into the future, the brighter the prospects for fusion energy shine. One thing is certain: the day will come when star power will no longer be a distant dream, but a reality within our reach. In the hidden corners of our universe lurks a silent force that sets everything around it in motion. Not light, not matter, but a mysterious entity that we have barely begun to unravel: dark energy. For many years, it has eluded the grasp of our best minds, gathering dust on the shelves of theoretical cosmology. Today, we stand on the threshold of revelation as new evidence suggests that we may have been mistaken about the very nature of this mysterious force. Could it be that what we thought was unchanging is actually changing before our eyes? Join us as we delve into the depths of space, guided by the latest data from the Dark Energy Spectroscopic Instrument, and embark on a journey that could redefine our understanding of the universe. To ensure we're all on the same page, let's first talk about baryonic acoustic oscillations, or BAO. These ripples, set in motion by intense pressure waves in the early universe, now serve as cosmic yardsticks, allowing astronomers to accurately measure vast cosmic distances. This complex cosmic interaction, a legacy from the birth of the universe after the Big Bang, provides us with a unique vantage point to scrutinize the fabric of the cosmos. In such a cosmic landscape, the Dark Energy Spectroscopic Instrument, also known as DESI, becomes a beacon of sorts. Armed with an array of 5,000 finely tuned fiber optic sensors, DESI is embarking on monumental tasks to meticulously map the three-dimensional positions of tens of millions of galaxies and quasars. This ambitious undertaking is designed not only to map the cosmic topography, but also to shed light on the shadowy force known as dark energy, which is believed to be the catalyst for the universe's accelerating expansion. Light is first reflected from the telescope's 15-ton primary mirror and then hits 6 large lenses that provide DESI with a wide, highly focused view of the sky, covering an area about 38 times the size of the full moon. These lenses are housed in a device that can be adjusted within millionths of a foot to keep the lenses aligned. After passing through the set of lenses, the light from the galaxy reaches the fiber optic cables at the DESI focal plane. At the very end of the telescope are 5,000 positioning robots, each carrying a single optical fiber, programmed to move to pre-selected sequences of galactic targets. This automated robot interaction allows DESI to target sequences of thousands of galaxies. Simultaneously, optical fibers that serve as DESI's eyes guide galaxy light down the length of the telescope to 10 spectrographs. These spectrographs are then used to obtain very accurate spectra of these objects and produce red colors for the various galaxies and quasars in the dataset. Each fiber optic sensor in the DESI array is a communication channel to the cosmos, guiding light from galaxies and quasars across billions of light years to the heart of the instrument. Robotic positioners ensure the jewel-like precision of each fiber's alignment to the celestial target. The fibers, each as thick as a human hair, are not just passive receivers. They are the endpoints of a complex optical path that begins in the depths of space and ends in the device's spectrograph. Here, the captured light is scattered into its constituent colors. When DESI scans the heavens, it picks up faint echoes of distant galaxies, each carrying a cosmic history recorded in BAO. These measurements, similar to the cosmic Morse code, are carefully decoded and analyzed to reconstruct the history of the expansion of the universe. Through this painstaking process, DESI provides a glimpse into the past epochs, tracing the evolution of the universe from its turbulent youth to its current, more measured expansion. The importance of BAO in this grand narrative cannot be overemphasized. Astronomers are using this instrument to map the expansion of the universe with unprecedented accuracy. This method, based on the fundamental physics of the early universe, offers a reliable basis for testing our understanding of cosmology by refining our models of the underlying structure and composition of the universe. Through the lens of DESI, BAO is transformed from a mere cosmic echo to a powerful discovery tool. So how will the mission help illuminate the darkest corners of space? So, let's elaborate on BAO. Imagine that the universe is a vast ocean in which sound waves once freely propagated through the hot, dense early cosmos. These were not sound waves as we know them, but rather pressure waves generated by the complex interaction between radiation and matter in the nascent universe. This interaction gave rise to what we now call baryonic acoustic oscillations, a relic pattern imprinted in the distribution of galaxies across the cosmos. These ripples in the fabric of the universe give us a standard ruler for measuring cosmic distances with extraordinary precision. In the early universe, there was a competition between gravity pulling matter together and radiation pressure pushing it apart, which created oscillations, akin to sound waves. When the universe cooled enough to form atoms and radiation separated from matter, these oscillations froze in place, leaving a noticeable pattern in the distribution of galaxies. The peak of these oscillations, at an interval of about 150 million light-years, serves as our cosmic ruler. This cosmic ruler allows astronomers to measure the expansion of the universe in a unique way. By examining the distance between galaxies and comparing it to the expected distance from the BAO, scientists can calculate how much the universe has expanded since light was emitted from these galaxies. This method also allows direct measurement of the rate of expansion of the universe at different epochs of time, which provides clues to the nature of dark energy and its impact on cosmic growth. In turn, the dark energy spectroscopic instrument can use BAO's measurements to produce an unprecedentedly detailed map of the expansion of the universe at different epochs, located atop the 6,880-foot summit of Mount Kitt in Tucson, Arizona, which offers panoramic views of space. DESI uses a battalion of robotic fiber optic sensors in its quest to understand the accelerating expansion of the universe. Peering into the night sky, the instrument captures the light of millions of galaxies and quasars. By measuring the red shift of the light from these celestial objects, DESI can determine how fast the universe has expanded at different times. The instrument's precision allows it to detect subtle BAO imprints in the large-scale structure of the universe, turning these measurements into a detailed three-dimensional map of cosmic expansion. This map is not just a collection of data points. It is a timeline of the history of the universe from its early, denser state to its current accelerated expansion. By comparing the observed BAO scale at different distances, and therefore at different times in the history of the universe, with what we expect from our cosmological models, DESI tests our understanding of dark energy and the fundamental nature of the cosmos. The beauty of the DESI approach lies in its ability to explore different epochs, offering a window into the expansion of the universe over billions of years. This huge period allows researchers to trace whether dark energy remains constant over time or evolves. So, what was the purpose of this study after all? As we know, the accelerating expansion of the universe, a phenomenon at odds with the expected slowing forces of gravity, has revealed the existence of a mysterious component known as dark energy. This discovery, made in the late 1990s through observations of distant type Ia supernovae, revolutionized our understanding of the cosmos. Dark energy, which makes up about 68% of the total energy content of the universe, has a repulsive force that opposes the gravitational pull of matter and thus accelerates cosmic expansion. It was she who laid the foundation for the lambda cold dark matter model, at a time when the disparate observed properties of the universe seemed mutually inconsistent, and there was no consensus on the composition of the energy density of the universe. The model successfully announced a wide range of astronomical phenomena, from the large-scale structure of the cosmos to anisotropy in the cosmic microwave background. Despite the complexity of the universe, the lambda cold dark matter model is relatively simple and characterized by a small set of parameters. These include the Hubble constant, the densities of dark matter and dark energy, and the initial conditions for the existence of the universe. The predictive power of the model allows astronomers to test its validity with observations such as the distribution of galaxies and the cosmic microwave background. The dark energy spectroscopic instrument has provided new insights into the mysterious nature of dark energy. By analyzing more than 6 million extragalactic objects at vast cosmic distances and different epochs, DESI provides reliable measurements of the expansion history of the universe with previously unattainable precision. This extensive data set, covering a redshift range from 0.1 to 4.2, allows us to reconstruct the expansion of the universe in detail and reveal the influence of dark energy throughout cosmic time. One of the most intriguing results from the first year of DESI observations is the indication that dark energy may not be a static force, but may evolve. This hypothesis stems from the subtle discrepancies observed between DESI measurements and the predictions of the lambda cold dark matter model. In particular, the data collected in this study suggests that the parameter of the dark energy equation of state is close to being consistent with the cosmological constant. However, if we extend the lambda model and add a time-varying dark energy equation of state, The DESI data in combination with the cosmic microwave background, or type Ia supernovae, definitely indicate a departure from the model. This means that the influence of dark energy may not be constant, but may change with time. This preference persists in different combinations of data sets, indicating deviations from the lambda model. The data obtained in the survey, especially the discovery of dark energy, poses a serious challenge to the lambda model. Traditionally based on the representation of dark energy as a constant component, the detailed mapping of the cosmic expansion history with the instrument provides data that may require modifications to the standard cosmological scheme. In particular, the parameters present-day value and rate of change of the dark energy, indicating the variation of the dark energy influence with time, indicate a deviation from the static lambda assumption of dark energy represented by the cosmological constant lambda, which requires a critical reassessment of the model's functions. The results of the paper have profound implications. If the dark energy equation of state does indeed change, this could lead to a major revision of our ideas about the expansion of the universe and its ultimate fate. Such a paradigm shift will not only refine our understanding of dark energy, but would also affect the broader cosmological models that describe the composition, structure, and evolution of the universe. To integrate these ideas, cosmologists may need to explore new theoretical frameworks or improve existing models to account for the time-varying dark energy component. This may require developing more sophisticated models that account for the dynamical behavior of dark energy, or revising our understanding of the interactions between dark energy, dark matter, and other cosmological parameters. One intriguing alternative is quintessence, a dynamic form of dark energy with a changing equation of state. Unlike the cosmological constant lambda, which remains constant throughout cosmic time, quintessence is a field that evolves, potentially providing clues to the observed divergence. Could the changing nature of dark energy be a manifestation of quintessence? This model allows the effects of dark energy to vary, potentially consistent with the evolving equation of the state of dark energy hinted at by the study. The possibility that dark energy interacts with dark matter or other components of the universe also opens up an exciting paradigm. Such an interaction could lead to observable effects on cosmic scales, potentially explaining the changing equation of the state of dark energy. Another intriguing but radical proposal is the concept of early dark energy. This model suggests that dark energy played an important role not only in the late universe but also in its early stages, leaving imprints on the anisotropy of the cosmic microwave background and large-scale structures. This may offer a new lens through which to interpret the findings, especially if dark energy effects have been woven into the fabric of the cosmos since its dawn. The viability of each of these theories depends on consistency with observational data at various scales, from CNB anisotropies to galaxy clustering and supernova luminosity distances. The contribution of this project lays the foundation for future research in cosmology, as DESI continues to produce an unprecedentedly detailed map of the cosmic web during its 5-year mission. It's expected to inspire several future projects aimed at delving deeper into cosmological mysteries. These future projects will likely build on DESI's findings, utilizing advanced observational techniques and theoretical models to further explore dark energy and its impact on the cosmos. A discussion between study participants Sheshadri Nadatharan and Adru Font Ribera emphasized the collaborative nature of this search, emphasizing the integration of DESI data with other observations to create a more complete picture of the evolution of the universe. Such a collaborative approach is essential to deepen our understanding of dark energy and its role in shaping the ultimate fate of the universe. Although the instrument's results challenge our current cosmological models, DESI's journey is far from over. It is merely a prologue to a much larger cosmological narrative, and standing at this threshold, we remind ourselves of how much we still have to learn about the structure of the universe. Imagine a place where the boundaries of reality blur, where the very fabric of the universe is stretched, and the unknowable becomes known. This is not a science fiction world, but a reality created deep underground, beneath the border between France and Switzerland. Here is the largest machine ever built by mankind, the Large Hadron Collider. It is a marvel not only of engineering, but also of ambition, and a testament to our quest to understand the universe at the most fundamental level. But could this device, designed to unlock the mysteries of particle physics, also be the key to opening portals to other dimensions? The idea of spatial portals may conjure up images of sci-fi gadgets and interstellar travel. Still, here at the European Organization for Nuclear Research, also known as CERN, they represent the gateway to revolutionary discoveries. Here, the concepts of space, time, and reality are intertwined thanks to the high-speed collisions of subatomic particles. This is not just a story about complex mechanisms and theoretical physics. It's a journey into the heart of what makes our universe move, made with the planet's largest and most powerful particle gas pedal. As we go deeper, we learn how these experiments not only challenge our understanding of the universe, but change it. CERN is nestled among the beautiful landscape of Europe, where the serene tranquility of nature meets human curiosity. The European Organization for Nuclear Research, the epitome of global cooperation, is home to scientists and engineers seeking to unravel the layers of our reality. CERN was founded in 1954 to unite nations in the pursuit of scientific knowledge, and has grown to become the world's largest particle physics laboratory. Here, more than 10,000 minds from over 100 countries converge to push the boundaries of human knowledge. The heart of the organization's research is located deep underground, the Large Hadron Collider, or LHC. This outstanding example of human ingenuity spans 17 miles, a circular tunnel in which the most advanced scientific experiments ever conceived are conducted. As the most powerful particle gas pedal on Earth, the LHC allows physicists to recreate the conditions that occurred moments after the Big Bang. By accelerating particles to near light speed and colliding them with each other, the LHC helps us explore the fundamental particles that are the building blocks of the universe. But CERN's role goes beyond particle physics. As a center of global scientific research, it is also a hotbed of technological advances. Innovations developed here, such as the World Wide Web, have fundamentally changed our world, illustrating how basic research by scientists has gone beyond the laboratory to impact society as a whole. This institution is more than a laboratory. Using the universal language of research and discovery, the European Organization for Nuclear Research brings people and countries together, demonstrating that our quest for knowledge knows no boundaries. If we delve deeper into the basic purpose of the Large Hadron Collider, we find that its true scientific excellence lies in the fact that it allows physicists to test and extend several fundamental theories of particle physics. This machine is as much about brute force as it is about precision and the subtle nuances of particle behavior at incredibly high energies. The standard model of particle physics, developed in the middle of the 20th century, describes the forces and particles that make up our universe. However, it is not complete. The LHC is a unique environment where particles collide at high enough energies to detect phenomena that can either confirm or refute this model. One of the key aspects of the research is the study of supersymmetry, the theory that every particle we know has a heavier superpartner. These partners, if they exist, could unlock many of the mysteries of the universe, including the nature of dark matter. The LHC also plays an important role in investigating the validity of string theory, a branch of theoretical physics that attempts to reconcile gravity with quantum mechanics. It suggests that point particles in particle physics can be replaced by one-dimensional strings. The vibrations of these strings appear to us as different particles. The energy levels achieved in this giant laboratory allow us to explore these ideas, potentially creating new particles predicted by string theory. But beyond the tangible, the LHC has entered the realm of what many consider science fiction. The idea of opening a portal is a term that's often misinterpreted by the sci-fi element of popular culture. Scientifically speaking, a portal is not a mystical gateway to another dimension, as shown in the movies or on television. Instead, it refers to the potential creation of microscopic black holes during particle collisions. These phenomena, predicted by the same string theory, would be extremely short-lived and would not pose a threat to our existence, as the sensational news of the yellow press suggests. While in pop culture, portals may be portrayed as doors to alternate realities or times, in the world of high-energy physics, they represent an opportunity to observe and study conditions in particles that can barely exist in the natural universe. These experiments have the potential to open up new dimensions of physics, literally. By analyzing the particles produced by these collisions, scientists can gather evidence that either confirms these theories or sends them back to the drawing board. With its unprecedented ability to test these theories, the LHC acts like a giant microscope, magnifying the very fabric of the universe and helping us understand the fundamental principles that govern everything we see and everything we don't. Particle physics is constantly evolving, and each experiment and discovery pushes the boundaries of our understanding of the universe. From discovering fundamental particles to challenging the limit of physics, the achievements of this research center are monumental. At the center of such scientific advances is the discovery of the Higgs boson, a particle integral to the mechanism that gives mass to elementary particles. Discovered in 2012, this breakthrough confirmed a crucial part of the standard model of particle physics and won the 2013 Nobel Prize in Physics. The existence of the Higgs boson, often called the God particle, has answered fundamental questions about how particles acquire mass. This discovery was a triumph of theoretical physics. Also of note is the recent public release of the discovery of the Higgs boson by the CMS collaboration, which marks a significant commitment to open science and collaborative research. Transparency fosters a global scientific dialogue in which hypotheses can be rigorously tested and new theories can emerge from shared knowledge. This release, which includes the unique combined software developed to search for the Higgs boson, allows scientists around the world to explore the intricate details of this monumental discovery. The resulting likelihood function with nearly 700 parameters captures the complexity of the experimental data, offering a multi-dimensional representation that defies even the most sophisticated visualizations. This openness not only democratizes access to cutting-edge science, but also enhances the collective ability to validate and build on key findings. But the journey did not end there. CERN has played a key role in other significant discoveries, such as the isolation of antimatter and the detailed study of quark-gluon plasma. a state of matter thought to have existed just after the Big Bang. Another experiment called ALPHA has successfully trapped anti-hydrogen atoms, opening a new way to study the properties of antimatter. This pioneering work aims to answer the question of why the universe is made up mostly of matter, even though the Big Bang Theory suggests there's an equal amount of matter and antimatter. Another cornerstone of CERN's research is the study of quark-gluon plasmas using the LHCb experiment. By studying quark-gluon interactions, scientists are delving into the study of the strong force, a fundamental force that holds atomic nuclei together. Each discovery at CERN not only adds a new layer to our understanding of particle physics, but also pushes the boundaries of what technology can achieve under such extreme conditions. These experiments require the precise coordination of hundreds of scientists and cutting-edge technology, reflecting the amazing collaboration of people around the world. As you may have realized by now, the LHC is not just a technology loop. It's a finely tuned experimental environment in which the most fundamental questions of physics are addressed. So, how does the Large Hadron Collider work? The process begins by feeding beams of protons into the collider from a chain of small gas petals. Each proton began its journey in a simple bottle of hydrogen, where electrons are stripped from it, leaving bare protons ready for acceleration. These protons pass through a series of gas petals, gaining energy at each stage until they finally arrive at LHC. Once in the collider, the proton beams are boosted to finite energy levels, reaching the 6.8 tera-electron volt mark during the latest 2024 launches. This intense energy is necessary for the protons to collide with sufficient force to decay into a range of subatomic particles, some of which may never have been observed before. The whole process takes place on a scale that's difficult to comprehend with everyday analogies, but we'll still try to explain the concept fully. 1 tera-electron volt is roughly equal to the kinetic energy of a flying mosquito. Thus, 6.8 TeV is akin to the total energy of about 6.8 flying mosquitoes. However, that energy is packed into a particle that is inconceivably smaller than a mosquito. The proton is a subatomic particle, meaning it's part of the nucleus of an atom and has a diameter of about 1 femtometer. By comparison, a mosquito is about 1/4 inch long. To visualize this difference, if a proton were the size of a pea, a mosquito would be the size of a large skyscraper. But all the energy of a moving skyscraper would be packed into such a small object. So let's continue. Of crucial importance in the whole process is the achievement of proton beam stability, a state when the beams are dense and well focused. The beams are carefully regulated or squeezed to ensure they collide in the detector at the point where they can be most effectively studied. This process involves precise control of the many magnets around the LHC ring that guide and focus the beams. The collider has already produced its first stable beams at unprecedented energy levels in 2024, marking the official start of this year's physics data collection season. The third year of LHC Run 3 promises 6 months of proton collisions with energies of 13.6 tera-electron volts at even higher luminosities than before, meaning more collisions for data-gathering experiments. This phase will be followed by experiments with lead ions, providing a different set of conditions to study. Also this year, the ATLAS experiment has already achieved a milestone in particle physics by measuring the width of the W boson for the first time. This parameter, crucial for understanding the weak force carried by the W boson, was found to be 2202 mega-electron volt, which agrees well with the predictions of the Standard Model. Moreover, at the forefront of investigating the fundamental asymmetries of our universe The LHCb collaboration has made significant progress in understanding the complex interplay between matter and antimatter. In recent experiments, they have studied the behavior of the neutral D meson and neutral strange B meson, uncovering new layers of complexity in how these particles violate charge parity symmetry. The neutral D meson, consisting of a charm quark and an up antiquark, has shown a peculiar quantum quirk. It can spontaneously transform into its antimatter counterpart and back again. This phenomenon's been captured with unprecedented precision in recent datasets from the first 2 LHC runs. The current study aims to identify potential CP violations in these transformations, which may shed light on the predominance of matter over antimatter in our universe. Similarly, the neutral strange B meson, consisting of a bottom antiquark and a strange quark, showed time-dependent CP violations when decaying into quark-gluon plasma. This observation marks a significant advance, as it was achieved with statistical significance beyond the typical discovery threshold in particle physics. These results not only confirm the known behavior of these particles, but also open new avenues of research. With the LHC now operating at higher luminosities, future data could further refine these measurements, potentially leading to new physics beyond the standard model that could explain dark matter and matter-antimatter asymmetry. In the vast universe of information surrounding the Large Hadron Collider, many myths and sensational stories have taken root. Today we'll try to clear up these misconceptions and explore the real scientific picture going on deep beneath the surface. One common myth is that experiments at the collider can inadvertently produce black holes capable of consuming the Earth. Now, while the LHC can create tiny black holes, they are on the quantum scale and evaporate almost instantaneously through a process known as Hawking radiation. Stephen Hawking's theoretical predictions convince us that these microscopic black holes pose no danger. They provide a fascinating insight into gravitational forces, but are far from the end-of-the-world scenarios depicted in science fiction. Another dramatic claim is that the collider opens portals to other dimensions or causes catastrophic natural disasters. Such scenarios, although popular in movies and on television, are not supported by any scientific data. The LHC's primary mission is to test the predictions of theoretical physics, to study the particles and forces at work in the universe, not to disrupt the fabric of reality as we know it. CERN operates under strict safety protocols. Comprehensive checks and risk assessments are carried out regularly to ensure that all experiments are safe, not only for scientists, but also for the environment. And finally, stories of supernatural phenomena or secret experiments are completely unfounded. As a transparent scientific organization, its research is published and available to the global scientific community. The commitment to openness extends to public documentation, accessible databases, and collaborative projects across continents. As we continue our journey, we want to remind ourselves to remember to rely on proven facts and scientific research. As we delve into the theoretical underpinnings of multidimensional research at CERN, we are exploring concepts that push the boundaries of our understanding of the universe. These areas of physics consider the possibility that our universe may not be limited to the 3 dimensions of space and 1 of time that we experience every day. The idea of higher dimensions comes from theories such as string theory and superstring theory, which both suggest that particles are not zero-dimensional points, but rather one-dimensional strings vibrating in multidimensional space. These theories suggest the existence of up to 10 or 11 dimensions, which may help resolve inconsistencies between quantum mechanics and general relativity. In practice, researchers at CERN use the Hadron Collider to investigate these higher dimensions indirectly. One approach is to look for signs of particles that may exist only in these higher dimensions, or effects such as the formation of microscopic black holes. The search for extra dimensions is not just a quest for knowledge about the fabric of space. It also has practical implications for understanding the fundamental forces of nature, including gravity. If extra dimensions do exist, they may explain why gravity is much weaker than other fundamental forces. Beyond theoretical curiosity, the study of higher dimensions can lead to technological advances in fields such as quantum computing and materials science, as these concepts push the development of new technologies to detect and measure extremely small and fast phenomena. As we delve deeper into the uncharted frontiers of particle physics, a new CERN initiative, the Search for Hidden Particles Project, or SHIP, is poised to revolutionize our understanding of the cosmos. The ambitious project aims to detect elusive ghost particles that may hint at higher dimensions beyond our three-dimensional space. The SHIP experiment is based on an innovative concept. Unlike traditional collisions at the LHC where particles smash into each other, SHIP will direct them toward a fixed target, increasing the probability of detection. The method is expected to be 1,000 times more sensitive than any existing equipment at CERN. These ghost particles, potentially constituting dark matter or other unknown aspects of dark energy, remain invisible under ordinary conditions because of their extremely weak interactions with ordinary matter. The implications of the discovery of such particles are profound and will probably change our fundamental theories of physics. Along with SHIP, plans are underway for a future circular collider, which should be a leap forward in particle collision technology. It is planned that this collider will reach its full potential by the middle of the 21st century and will push the boundaries of human technology and scientific research. Potential discoveries made at SHIP and the future circular collider could open new chapters in the history of our universe, from advancing our understanding of fundamental particles to creating new technologies. The implications to go far beyond particle physics, promising a glimpse into the very fabric of the cosmos and perhaps even into the higher dimensions that weave it together. As CERN continues to support its scientific achievements, the quest for knowledge is moving forward, promising a future in which the mysteries of the universe will be revealed one collision at a time.